Hello and welcome to part 5 of Dev Maths and Stats Refresher Course Lecture 3, where we move on to some applications of partial differentiation in this section. So in economics, for example, we might find the marginal product, the marginal cost, marginal revenue, elasticities, comparative static analysis of equilibria, and so on. So let's take these one by one. So marginal product, marginal cost, marginal revenue. I think we've already mentioned this. Let's open this part up. So if you had a very simple model of any process, you might say that output, costs, revenue, these things depend on a single variable, like labour hours. And then, as we saw in the last lecture, if you differentiate that, you then get the marginal product. So how much extra production do you get with an extra hour of labour? And so on. With partial differentiation, do the same thing, but now we can deal with this realistic situation where the things we're interested in depend on several different factors. For example, if you're talking about production, maybe in agriculture, that's often modelled as a function of these three variables here: land, labour and capital, where N stands for natural resources, land, labour, capital. So you write like this, production function. So if that's total production, then Fn will be the marginal product of land. That's the extra bit of production you get if you get an extra unit of land, with the other two inputs remaining fixed. And FL is the marginal product of labour. So if you have a bit more labour with the same amount of land, the same amount of capital, and so on. And FK is marginal product of capital. So let's do more of a kind of impact type analysis using a project example. So the costs of a project depend on some factors. You could put your own factors in, but here are some realistic ones: number of people you're trying to work with, number of people you're employing, and then some sort of input cost like equipment. So it could be fuel or other sorts of inputs like computers or whatever. So the cost function, maybe you think it looks like something like this, and hopefully you can recognise the form of this. Pause to think about it. And the name of this is a Cobb-Douglas function, or it's a pure Cobb-Douglas function. These should add to 1, but this is a Cobb-Douglas type function. So it's going to have diminishing returns to labour and diminishing returns to the price. Oh, sorry, this should say b to the power half. It's simplified it. So b to the power half is diminishing returns to the beneficiary numbers. So we can find an expression for the marginal cost, MCB, of increasing the number of beneficiaries by partially differentiate this with respect to B. You should see what's happened here. Right, so you should be able to do this by hand, but it makes it slightly harder, but it shows it in this form. So this, remember, is b to the power 0.5. So these things here are being fixed because we are taking marginal cost of increasing beneficiaries. So we want to differentiate with respect to b. So L and P are fixed numbers, so these things stay the same. Then you must multiply by 0.5 because square root of b means b power 0.5. So 0.5 multiplied by 150 is 75. And then b power half subtract 1 becomes b power negative half. So this here is b power negative half, or 1 divided by b to the power half, square root of b. Let's have a look at the other two partial derivatives. Marginal cost with respect to labour and with respect to price of equipment, something like this. So again, you should be able to see what's happened here with the L. So 0.4, so this stays constant and this stays constant. 0.4 times 150 is 60. Then 0.4 subtract 1 is negative 0.6, so then 0.6 comes to here. And similarly for partial derivative with respect to P. Once you've got all these equations, the total cost and then the partial derivatives, the marginal costs, you can answer things like this. So suppose you've got a project and you're assisting 13,220 beneficiaries. Price of equipment is $2.50. Oh, and you're employing 35 people. Then you can find what's the total project cost? What's the marginal cost of employing one more person? Marginal cost of employing an extra staff member, marginal cost of assisting another person of employing an extra staff member and an equipment price rise. So first of all, put these numbers into the total cost function at the top. So it's substituting them into the first equation, total cost, and you just get this. So that's using the thing you've been given at the start. So in order to assist this many people with the price of equipment at this much, employ this many people, it's going to cost you $94,127. It doesn't say what units. Oh, dollars, yes, dollars. Then what's the marginal cost of assisting one more person? So then you put these same numbers into this equation, the partial derivative with respect to B, and you find that that would cost you, okay, that would cost an extra $3.56 to assist one extra person. How much will it cost to employ an extra person? Well, you put this into this one here. That will cost you an extra $1,075. How much will it affect your total cost if the price of equipment went up by $1? That's the last marginal. That will cost $11,295. So if you compare the three answers, which possible source of cost increase has the greatest marginal effect? Not this one by some way, yeah. So the greatest marginal effect is an increase in the price of equipment. So a $1 increase in the price of equipment would give you a $11,300 increase in costs, compared to only a $3.50 increase in costs if there's an increase in beneficiaries by 1. So we had to do all this work to get that, to figure that out. But if we look back at the original cost function, it's not easy to tell from the cost function that this would give us the biggest impact and this would give us the smallest impact, and this would be between it. It's not easy to tell that from the original function. You have to do this calculation to work that out. Yeah, so thanks for watching.